This lesson covers some of the important differences between bits and instructions. This is where we left off with our last lesson. Before we get started, let's add in a simple rung. And now watch this area as we add in another output device. Here we've got a new set of contacts and a new output, lamp F, on our light box to use for our examples. And of course we'll need a new bit for lamp F, and notice that the bit just happens to contain a status of 1. This time we'll use the actual address O:001/1 for the bit instead of a symbol or nickname. The transfer of information from the bit to the output contacts will be handled on step number 3 of our scan cycle. This is pretty straightforward so far. Even so, some students have misconceptions about it. They wonder, how can the device in the field be on if we don't have an output coil anywhere in the program to energize it? One way is just to manually type the 1 into the bit box ourselves. We'll talk more about this in another lesson coming up. For now, just watch this area and we'll add in another input device. And here we've wired up a set of real-world contacts for switch B on our light box. And naturally, we'll need a bit to store the status for the switch. And the address will be I:000/1. The transfer of information from the switch to the bit will be handled on step number 1 of the scan cycle. And now switch B is available to use in our examples. And now let's add another simple rung. We'll need an address for this instruction. And let's say that we decide to use the address O:001/1 for the new output device, lamp F, that we just wired up a few minutes ago. And the address for this instruction will be switch A again, not our new switch B the way you might have guessed. And naturally, the new rung will be executed as part of step number 2 in the scan cycle. And basically what we're doing here is just adding in more ammunition to use for the examples that are coming up. Now let's highlight some of the items in our sketch. Notice that 4 are highlighted in blue and 4 are highlighted in yellow. Take a good look, and now we've removed everything except the highlighted items and the processor that they're located in. We'll focus on the blue items first, and notice that each one of these is a box, and that each box contains either a 1 or a 0, which fits in perfectly with our definition of a bit. In other words, each one of the blue items is a bit or a box located inside our PLC processor. Now let's focus on the items that we've highlighted in yellow. These are instructions or commands located in the ladder logic program. And here they are together. Unfortunately, many people and some official books confuse the two terms bits and instructions. Maybe that's because they share the same address assignments. But regardless, bits do one job and instructions do another job. You need to understand the differences between them. And here's what they'll look like in the RS Logic software. Instructions live in the ladder program, and you can access the bits by opening up the data files. Many of your hands-on troubleshooting exercises in the boot camp will involve forcing inputs and outputs and toggling bits, and understanding the effects those operations have on various instructions in the ladder program. Now let's go back to our sketch and add another bit or two. Here's a bit, a box, with the address B3/0, and one more, T4:0/DN, and this is where we'll leave our setup, for now at least. Now let's go back to a simple idea and see what some people do to make it needlessly complicated. Remember that a bit box can hold either a 1 or it can hold a 0. Now that's simple, but some people insist on saying that 1 equals true and that 0 equals false. That just leads to a lot of confusion down the road. Why make it complicated? Just stick with 1s and 0s. After all, that's exactly what you're going to see when you monitor the bits in the software, not trues and not falses. Other people want to use the terms high and low instead of 1 and 0. And again, that's just making a simple thing more complicated than it needs to be. Then there are some people who assume that 1 means on and 0 means off. That's another beginner level misconception, one that does not always work in the real world. Now this last one that we'll cover is slightly different. There are some people who say that 1 equals set and that 0 equals reset. That way of looking at the bit status does cause confusion, but we'll have to learn to live with it anyway. That's because the terms set and reset are used in many of the official books. Everything considered, the best rule is the simplest rule, and that's the one we started out with. So a bit is a box that can hold either a 1 or a 0, and that's a rule to remember. Now, here's another idea about bits and instructions. Suppose that we have a real physical device named switch R wired up in the field. We'll keep things simple by not showing the wiring, but it's there. Now consider that we've also got a bit, a box, named switch R located inside the processor. And we've also got an instruction addressed as switch R inside the processor as part of the PLC's ladder program. So, like it or not, that gives us 3 separate things, and each one is called switch R. We'll learn exactly what this piece of the puzzle does in our next lesson. But for now, let's just say that it's got to be tied to either the switch in the field or to the bit inside the processor. So which do you think it's going to be? Many technicians, even some with years of experience, are thoroughly convinced that the instruction in the program is tied to the actual device located out in the field. That's a very common misconception. It's so common, in fact, that many PLC schools teach that approach. But it's wrong. Actually, the instruction is tied to the bit located inside the processor and not to the device located out in the field. Now, for this next discussion, we've shifted things to the right to give us some room to troubleshoot a simple wiring problem. Many people explain the status of an input bit by saying that when the switch is on, the bit contains a 1, and when the switch is off, the bit contains a 0. That explanation usually works okay until a problem comes along. Here we've got a problem. The neutral wire is broken, and that's why the bit contains a 0, even though the switch is in the on position. When you get right down to it, that old switch on 1, switch off 0 rule just doesn't work for troubleshooting purposes. That's why we never use it in our boot camp classes, since troubleshooting is a big part of what we teach. Rather than the switch position, some people go by the voltage signal instead. There's nothing wrong with that approach for troubleshooting as long as you set up the voltage test correctly, the way we have it here. The 0 volts reading shows that there's something wrong with the input circuit, and that's why we have a 0 in the bit, even with the switch turned on. Setting up the meter like this can lead to some incorrect conclusions, unless you really stay on your toes. It's fairly common practice for a technician to clip one of the voltmeter leads to a known neutral connection and then move the other probe from one point to another while looking for voltage. Quite a few technicians have been tricked by this setup. Their line of reasoning usually goes like this. Okay, I've got a good voltage signal coming into the module, so the switch and the wiring must be okay, but the bit still won't change to a 1, so the input module must be bad. That's a mistake. Using a milliamp meter for testing is harder to do since it has to be connected in series with the input circuit, but the test is usually more conclusive. Notice that no current on the meter explains the 0 status of the bit. We'll cover all of these ideas in more detail when you go through the class. Here we've fixed the broken wire, and now the on position of the switch does give us a 1 in the bit. Different input modules have different specifications for on and for off signals. The meter readings we're showing here are pretty typical for the type of hardware we're using for our video lessons. And here's where we stand so far. The sketch is starting to look a little crowded, but since we're covering everything step by step, all of the pieces of the puzzle should be falling into place for you. If not, you can always just watch the videos again for a quick review. The main thing that we're developing throughout all of these lessons is a mental image, a picture in your head, of a left to right flow of signals through the PLC. Each one of these arrows represents a change in the signal from one form to another. This detailed, systematic method of teaching PLCs is one of the main reasons why our boot camp approach is so effective, even for students who've been through other training programs with poor results. And now we're ready for the next lesson.